The fixed effects model can be estimated using the least squares dummy variable or LSDV approach. It is one of the methods used in panel data analysis to control for unobserved heterogeneity. As discussed in the previous tutorial, unobserved heterogeneity refers to characteristics that are unique to each entity such as individuals, firms, or countries and do not change over time. These are also known as individual-specific effects. Or, these could be characteristics that are unique to a time period and do not change across entities, and are known as time-specific effects. These unobserved individual and time-specific characteristics might influence the dependent variable, leading to biased estimates if not properly controlled. The LSDV model can account for individual-specific as well as time-specific characteristics, allowing researchers to isolate the effect of unobserved heterogeneity. The LSDV model uses dummy variables to introduce a separate intercept for each entity and each time period. With separate intercept for each, these dummy variables account for the unique characteristics of each entity or time period. Therefore, it allows us to control for unique unobserved characteristics of entities or time periods. For illustration, let us consider a basic Keynesian type of consumption function with consumption as the dependent and income as the independent variable. In the equation shown here, we have I individuals or cross-sectional units and T time periods in the panel data. Estimating this equation implies a pooled OLS model without controlling for heterogeneity. However, pooled OLS will likely lead to biased results because the model does not control for unique characteristics of individuals. Each individual is unique, with unique traits, preferences, and characteristics that will influence consumption. As an example, these characteristics could include gender, race, risk aversion, tendency to be miserly, and so on. These characteristics stay constant over time, but they vary across individuals. Hence, we must include individual-specific effects to control for these characteristics. Suppose we decide to include both individual-specific and time-specific effects in the consumption function shown earlier. Then, we can specify the LSDV model as shown here. The dependent variable of consumption and the income variable stay as they are. In addition to these, we include cross-sectional and time-specific dummy variables as independent variables in the models. The first set of dummy variables are the cross-sectional dummies, which account for individual-specific heterogeneity. The number of cross-sectional dummy variables is equal to I-1, that is, 1 less than the total number of individuals or cross-sectional units. Hence, one individual acts as the base and all the other individuals are assigned a dummy variable which gives them a unique intercept. The second set of dummy variables are time-specific dummies that account for time-specific heterogeneity. Again, the number of time dummies is 1 less than the total number of time periods, that is, T-1. Similarly, one time period acts as the base and all the other time periods are assigned a dummy variable. To make the specification clearer, let us assume that we have data on 3 individuals A, B, and C across 2 time periods, T0 and T1. It is important to note here that in practice, we need more data for a reliable estimation. We are considering 3 individuals and 2 time periods only for illustration. Furthermore, we wish to include individual as well as time-specific effects in the model. Then, we can specify the fixed effects model with LSDV approach as shown here. CIT refers to consumption and YIT is income as usual. The dummy variables dB and dC represent the individual-specific effects and T1 represents the time-specific effects. We have 3 individuals in the dataset and 2 individual-specific dummy variables. Individual A acts as the base and the other 2 individuals B and C have their own dummy variables dB and dC respectively. These dummies dB and dC will capture the unique time-invariant characteristics of the individuals. That is, they will account for the individual characteristics that do not change over time. Similarly, time period T0 acts as the base and the period T1 has its own dummy variable in the model. This T1 dummy will capture the characteristics unique to that time period. It will account for time-specific characteristics that do not change across individuals. It is also possible to include only individual-specific effects or only time-specific effects in the model. It is not necessary to include both individual and time dummies. Moreover, the number of dummy variables is one less than the number of cross-sections or time periods to avoid the dummy variable trap. If the dummy variables are equal to the cross-sections or time periods, then they will predict each other perfectly. That is, it will lead to perfectly collinear variables and problems in estimation. Earlier, we mentioned that the LSDV model allows us to introduce separate intercepts for each entity and time period. Let us continue with the same example to illustrate this. As discussed earlier, dB and dC are individual-specific dummy variables and T1 is a time-specific dummy. Individual A and time period T0 act as the base. The intercept or constant alpha 0 represents the base individual and base time period. Hence, alpha 0 is the intercept of individual A at time period T0. The coefficient alpha 1 is associated with individual B. As a result, the intercept for individual B at time period T0 will be equal to the base alpha 0 plus alpha 1. Similarly, the intercept for individual B at time period T1 will be equal to the base alpha 0 plus alpha 1 plus theta 1. This is because the coefficient theta 1 is associated with time period T1 and alpha 1 is associated with the individual B. In the same way, we can add alpha 2 instead of alpha 1 if we want to know the unique intercept of individual C. Therefore, every individual and every time period can have a unique intercept in the LSDV approach. These unique intercepts account for the heterogeneity of entities and time periods. This fixed effects model using LSDV approach is estimated using OLS after introducing the necessary dummy variables. Moreover, the coefficients from the LSDV approach are identical to the coefficients estimated from the fixed effects within estimator. However, the LSDV approach has some serious disadvantages or drawbacks. Firstly, the LSDV model can consume a lot of degrees of freedom. We have to include dummy variables for each entity or each time period. With increase in the number of entities or time periods, the degrees of freedom fall rapidly. This can be problematic because we might end up with too many independent variables to estimate the model. Suppose we have data on 200 individuals. Then, we will have to include 200 dummy variables for individual specific effects in the LSDV approach. The model will end up estimating 200 additional coefficients. This not only consumes a lot of degrees of freedom, but can also cause problems with multicollinearity. This is because we are including a huge number of dummy variables which might be highly collinear. Secondly, we cannot include time-invariant independent variables in the model. Time-invariant variables are those that do not change over time. These could include variables like gender, race, and so on. These time-invariant variables become perfectly collinear with the individual-specific dummy variables included in the LSDV model. As a result, these time-invariant variables are automatically omitted from the model. We cannot explicitly include these time-invariant variables as independent variables in a fixed effects model. Instead, the individual-specific dummies in the LSDV model automatically account for all these time-invariant characteristics. Therefore, if we are specifically interested in analyzing the effects of such time-invariant variables, we cannot accomplish it with a fixed effects model. Just like we cannot include time-invariant variables along with individual-specific effects, we also cannot include entity-invariant variables along with time-specific effects. Entity-invariant variables are ones that stay constant across all individuals, for example, a policy that is applicable to every individual or cross-sectional unit in the data. The time-specific effects become perfectly collinear with entity-invariant variables and cannot be included in the model explicitly. Instead, the time-specific effects automatically absorb all such characteristics that are constant across individuals and vary over time. Thank you for watching, and I will see you in the next tutorial.